and this is my entry into the advanced programming section of the competition. So this is my C compiler. It's the ANSI C variant, namely, but it does, parts of it will support C++, but in its entirety it can't. So it's a compiler, which means it's going from high level to low level. And the plan in the end is to go from high level being C down to assembly, which is going to be an ARM64, as this is running on a M1 Mac. So it's the Apple Silicon version of assembly I want it to get down to, is the plan. At the moment, it's not completely finished. It's going to a stage called intermediate code generation, where it's making LLVM, which is a quite general intermediate representation of the code, which is very close to assembly, but it's platform independent, which means that it will go through the compiler to that stage, and then you could go to whatever you want. So you could go to RISC version 5 or ARM64 or x86 or whatever you wanted from there. So it's not specific at all. But the stage going to assembly I haven't completed yet. So this is the main program here. So as you can see, this bit's quite short, but there's a lot more bulk to it in the rest of it. So we're going to make a program here. Depending on how familiar you are with C, this will make more or less sense. So we're going to make a function which is going to return an integer value called main, and that's the first function which will get called. So in C, main is just the main function, very similar in other languages. And then we use these curly brackets or braces, which denote a scoping calculation, and everything inside of that is part of that function in essence. So then, as just a test to show it's working, we're going to make a variable, call it x, and that will work in itself, but just to add a bit more complexity to it. Well, it's still not awfully complex, but it's just makes it a bit more interesting. We're going to make it equal to 0. Further along, I'll add some more into that test program file, just to make it a little bit more interesting and show a bit more going through. So we've made that there, and then I'm going to run my program here, and I'm going to show what's output from what's called the lexer. So the lexer is this bit here, and it's in this code here. I would run through this, but I don't really want to spend too much time on it, as it's not too important, and they're quite big programs to run through. So I'll go through the basics of them. So here I'm going to do dump tokens, and the lex is making tokens, which are what you can see here. The location is in the magenta, and in the yellow is what's the token string part of it is, and in the cyan is what type of token it is. So it's making the symbols into something more helpful, numbers into something more helpful, and identifiers, so a variable identifier, more helpful, along with types. So it's just making it easier to work with, basically. The next stage is going to go into syntax analyzer, which is, I'm in the wrong code here. So it has a symbol table which contains all the variables, and it has an AST, so an abstracted syntax tree, which is what I'm about to show you, and it's taken in the lexer, and it's going to call that function which makes the tokens. So the lexer here, if I do dump AST, that's the abstracted syntax tree, which I shall explain. So the translation unit is each file. Function declaration is quite obvious, a function declaration. Then a variable declaration is just showing what that function's called, basically. Then it's got no argument, so the argument list is empty. Compound statement, so all the functions in there are going to be in that compound statement, and that's going to be all the different things you have. Initialization statement is going to have another variable declaration of an int and an x, and then the assignment operator is an equals, and then it's got an expression with an operand of 0, which is just saying make x and then equate it to 0. That's the basics of it, and it's using a recursive descent parser, which uses all these functions which return booleans values to work out what fits correctly there. And this makes it more helpful because you can then check the syntax of it. So if I miss out this semicolon here, it will then look through it and it will notice error missing semicolon on line 73. And on line 73, as I just did, I removed the semicolon. So it makes it helpful because it can find all these errors and it can fix it for you. So as you can see, it did error recovery, which is basically where you put in place what you think should be there, even if you don't know what it actually is. So it put in place the semicolon there because it thought it probably would go there. And now equally, it will work out what variable you meant if you typed it wrong. So if I make one called ABC, which is just an identifier for a variable, and I set it to 1, and I make one called, so say I made a spelling mistake, so I'm going to name this one Y, and I want it to equal ABC, but I made a mistake and I wrote QBC. Now that shouldn't compile technically, but if we run it through here, it will then tell you what you probably meant to say. So it said use of undeclared variable QBC on line 75, and as you can see, line 75, it's not been declared QBC, there is no QBC. It said you may have meant ABC, and it's then replaced it with ABC in the syntax tree so that it can carry on going and it can find more errors which you may have made later on, which means that each time you compile, it's going to be more helpful, because if you only get one error message and you've got 5 errors, you're going to have to fix it, and then it might end up being a problem with something later on, which is why it's broken in the first place. So it's just makes it a bit more helpful, to be honest. I'm going to get rid of those again and just leave it as it was. Semantic analyzer is what comes next. So that takes in this big tree here, which we made last time, and is going to check the semantics. So the semantics are the types. So if it's an integer, it can't take hold of a struct, so that's a data structure which contains a boolean and a float, for example. Let me give you an example in this code. So if I had a struct named B and I took in L and a boolean called Y, I couldn't then decide that I might make this called B, Y. So that's going to make this struct called B and name it. Actually, let's not name it Y. That's a bit silly. Let's just name it temporary. Yeah. If I then try to set that to temporary, these are all arbitrary, those letters. It's just for an example. If I try to set X equal to temporary, then it's not going to work because they're not the same type. So that's what the semantic analyzer is doing. Let me just remove that and leave it as it was. So after it's done that, it's then got this big tree here, and it needs to make code from that. So the way it's going to make code is in this intermediate code generator here. So this is quite a big program, and this is what's making the LLVM. So I don't know if I said it earlier, but LLVM is what Clang, G++, GCC use as an intermediate representation of the code. So before you go to assembly language, you go to this. So then platform independent optimizations will occur there. So just general stuff, not very descriptive stuff. What do I mean? Just general optimizations. For example, if you made x equal to 0, then you made x equal to 0 again, whatever your computer you're targeting this at, it's obvious that you've already set it to 0, so why set it to 0 again? It's that sort of thing which you would optimize for. And this is as far as I've got with the project. I've run out of time to do any more, but I'll still be carrying on with it and hoping to get it to a point where it is a fully functioning compiler. So here it is making the code. So when it's making the code here, it's going through each of these parts and just looking at what it needs to do. It's a little bit hard to describe, so sorry for it not being a very good explanation, but it's going through each of these are called non-terminals and terminals. So it's going through each one of them, and it's kind of got a template of what it should look like, and then it's going and seeing the next one, and then that one's got a template of what it should look like, and keeps on inserting it. sorry for the bad explanation. If you Google code generation from an abstracted syntax tree, you might get a better way of wording, if that makes sense. I apologize. So this is what it's creating, and then it is got a final stage, which is the code generation, which I'm just about to show you. So uh, with my program, you can write dump IC, so dump intermediate code, and that's going to show you the intermediate code. So here, this is LLVM. Okay, so I'm going to make a program to run in it and test it against what Clang's producing for its intermediate code, and just to prove that it's working, basically. It's more easy if you have a play around with the compiler itself. It's quite hard to demonstrate, annoyingly. So we've got our x initialized, and I'm going to make a while loop, and the while loop's going to go while x is less than 5. So this is a very basic program, and then it's going to make x increment until it equals 5. So it's just going to make x equal 5 in the end. And here we go, we're going to run it. So I have written this up here, which is going to dump the tokens from the lexer, the abstracted syntax tree from the syntax analyzer and the semantic analyzer, and the intermediate code, which is what is here. And this is what Clang's outputting. So I'm just going to show you what Clang's outputting. Clang's creating a temporary variable, which mine isn't doing yet, which is what this extra code in here is doing. But the basics of it are very similar, and both of them will produce valid assembly code. So I'm just showing that here to show them virtually matching up. I'm using a subvariant of LLVM, so I'm not using all of the functionality of it, just to remove some complexity from it when converting to assembly, because I don't think that I need it, but that may change later. So you can see 1 is going to be a pointer to x, then it's allocating 4 bytes long in memory for an int to be stored. It's then storing 0 in where 1 is in memory. It's then making 2, which is going to be a register, and it's putting the value of whatever is in 1, which is x, into 2, which is going to be a register. It's then comparing what's in 2 against 5, and then putting it in another register, or what potentially could be a register, which is what 3 denotes. It then does a branch of whether it's, and if that 3 was true, so if what was in 3 was true, it's going to branch, and if it's true, it's going to go to WLB, so while loop body, which is that section there. If it's false, it'll go to WLE, while loop end, at the bottom there. And then it's going to jump back, it's going to go here, and it's going to add 1 to x, and then branch back up to WLS, which is the while loop start. And that's basically it. So that is my C compiler for ANSI C and producing LLVM.